We really want to extract this hidden symmetry in quantum theory while preserving the ability to perform quantum computation like transformations. My initial interest was to understand how the universal computer can be generalized as a universal constructor. And I was really struck by it. They are like guiding principles that should also help us guess future theories of physics. There are some sets of states that cannot be all copied perfectly by the same machine. This system that may not obey quantum theory, but has features of quantum physics in it. Post-quantum theories may also have this feature that you can derive their probabilistic behavior from an underlying deterministic dynamics, which is interesting, I think, in itself. The interoperability of information is a way to express a property that we expect in most information carrying systems. So we usually assume it's there, but no one had bothered expressing it formally before. If gravity can entangle two masses, then gravity must be quantum. And it's quite elegant. You just put this requirement of what tasks you want to be possible on these two systems. If you decide to abandon this principle, you would have to think very hard to imagine even how to measure a single observable on a system. Understanding what a mind is doing when it's thinking would benefit a lot from some of these physics and information theory-based approaches. They are the fuel for future discoveries. I think that's where fuel for even future applications comes from. We need to keep the fire alive there so that new ideas can come out.
Hello, everyone. Thanks for joining us today. Today, I'm pleased to have Chiara Marletto joining us for a discussion about the constructor theory of information. And Chiara Marletto is a researcher in the University of Oxford, researching the foundations of physics and also lots of aspects of quantum physics, but also ideas beyond quantum physics as well, which we'll be talking about today. So thanks to everyone for tuning into this discussion, and thanks, Chiara, for joining us today.
Yeah, thanks, Maria, for having me.
Great. So I think a nice place to start is to talk a bit about how you ended up doing research in this area, and in particular on constructor theory. And we'll talk more about what constructor theory is in a bit. But yeah, how did you end up starting to research these things?
Yeah, I think it was a path of casual encounters as well as more directed choices on my part. So initially, I think I was really interested in understanding quantum. I like quantum information, so I think that's what I thought I would do when I came here to Oxford for a PhD. And then so my initial interest was to understand how the universal computer can be generalized as a universal constructor. So I was interested already in the works by von Neumann on this topic, where he, as we will say probably later, he tried to think of something more general than the universal quantum, actually a universal computer in the sense of Turing. And then he landed on this idea of the universal constructor. But I didn't know that at the time David Deutsch had a theory that was just in its infancy at the time, and he was thinking of exactly doing this. So then in first year of my PhD, I started working on a number of topics in quantum information. And then finally, I heard this seminar that David gave at the physics department. And I was really struck by it because I was really interested in these topics. And he really gave a talk on constructor theory. So I thought, wow, that's great. So I started chatting to David through Arthur, who was my supervisor, He introduced me to David. And then we had a nice discussion with David about the topic. And that's it. That's how I started, I chose the topic, or actually rather the topic of my thesis chose me in a sense, right? So I ended up really liking this thing. And initially I was telling Arthur that this would be like an aside, maybe like a curiosity in my thesis, while having more sort of standard topics in quantum information, maybe algorithms and so on.
Right.
And in the end, actually, that wasn't the case. The thesis ended up being almost all on constructor theory and its applications to information. And what I found promising about the theory was exactly this, that it connected the original spirit that was there at the start of quantum information, where people were interested in understanding the foundations of the quantum physics through information theory, with a new effort now in the direction of understanding constructors, not just computers, but always focused on this idea of fundamentals problems in physics, which I think quantum information theory at present has forgotten a little bit. So if you arrive in the field and you want to understand fundamental problems, it's difficult to do that in the current quantum computation mainstream set of topics. But this was ideal because it really took me a little bit out of it and trying to extend beyond what had been already done. And I thought this was perfect. So that's how I ended up doing this.
Mm-hmm. Yeah, great. Yeah, it's cool to hear how you unexpectedly converged onto constructor theory becoming the main topic of your PhD research. And yeah, we should talk more in a bit about how you can now look at these fundamental problems that maybe standard quantum information theory is partly forgotten about in some way.
Yeah.
So yeah, before we get onto that, can you give us a kind of overview of what constructor theory is and the constructors that you mentioned as well?
Yeah, so I guess the best way to think about constructor theory at the moment is that it's a program of research based on a number of hopes, as well as also some results that we've had so far. But I think initially it was intended, at least by David when he proposed the philosophical foundations of the theory, as a way to generalize the quantum theory of computation beyond quantum computers. So to cover these more general machines that von Neumann had devised actually quite a while ago in the 50s. He thought of this idea of a programmable machine that doesn't just perform computations, but can perform any kind of physical task. So transformations like thermodynamical transformations, chemical transformations that are relevant for biological systems, and any kind of transformations that involve substrates being changed from one form to another under the given laws of physics. So von Neumann had this idea, and he defined a universal constructor, which is a natural generalization of a universal computer. So it's a programmable constructor that can perform any physically allowed task. And constructor theory ultimately should be the theory of these machines, the same way that the theory of computation, both classical and quantum, is a theory of the universal computers, classical and quantum. And the thing that's more subtle in what constructor theory really is that just like for the quantum theory of information, understanding the repertoire of a quantum computer, of a universal quantum computer, allows you to understand better quantum theory itself. Also with constructor theory, understanding the physical limitations on the repertoire of a universal constructor is isomorphic, if you like, is the same as studying the principles that tell us what is possible and what is not possible under the laws of physics that we have. The hope and the vision behind constructor theory is that by expressing laws in terms of what tasks are possible, what tasks are impossible, and why, you can then also express new physical principles that supplement the current laws as we know them and allow us to understand them in a deeper sense. And in fact, the early works on constructor theory, which is what we've been doing so far, and particularly the applications of these ideas of switching from dynamical laws to statements about possible and impossible tasks, the early results from this approach that I've been developing myself are exactly of this kind. So they are not really in the direction of create. So they haven't mentioned the universal constructor yet, but it's more like trying to understand these principles expressed in terms of possible and impossible tasks, formulate them in various areas of physics where there are open problems, and try to use them to fix some of the issues that we have with dynamical laws. For example, something you also like, the tension between thermodynamic reversibility and the reversibility of dynamical laws, or understanding how information theory ties in with fundamental dynamics and how, for example, you can phrase laws about information that are independent of the specific dynamics, whether classical or quantum, and then also understanding some properties of the physics of life, etc. So I think these are the two ways in which you can think about constructor theory right now. And it's a program, so we're pushing the boundaries and trying to bring along new results in this framework.
Yeah, cool. So to focus a bit more on information specifically, so after the kind of first paper where David did the philosophy of constructor theory, the next one was this constructor theory of information paper that you wrote together. So could you tell us a bit about how constructor theory applies to information and what it tells us about information and what problems might be solved by using the constructor theory version of information rather than classical and quantum information theory?
Yeah, so I think the aim of that work that I did together with David was to find a first application of this switch from dynamical laws to statements about possible and impossible tasks. That was one aspect. And the other was to provide some foundations to theories of information as currently understood. So as you said, classical information theory and quantum information theories both exist. But if you look at, for example, quantum information theory, unlike classical information theory, it is phrased in a very dynamics-dependent way. So if you open like a textbook on quantum information theory, you will see that it's basically quantum physics. The Schrödinger equation or the Heisenberg equation of motion are used to prove theorems. And so lots of features of quantum theory, like unitarity and Hilbert spaces, etc., all of the formalism is used heavily in showing results about channel capacity, about no cloning, etc., etc. It's, as a theory of information, is not very satisfactory because information is a concept that exists at a higher level of abstraction than a specific dynamical theory. And so we wanted to provide a foundation for both classical information theory and quantum information theory, where we're not relying on a specific dynamical law to talk about these concepts. And finally, what we thought was interesting was that instead of attempting to define information, which is what sometimes you find in there's works on these topics, what we wanted to do to root it within physics, to root information within the physical laws, was to express regularities that a given physical system must have in order to be able to carry what we usually informally call information. And this something that hadn't been done before. We often assume about a bit, for example, that it must have certain properties, but we never express what those are in terms of, say, requirements, formal requirements on the kind of transformations we should be able to perform on it. And so with the laws of constructor theory of information, the principles that it suggested, that proposed, we wanted exactly to address this issue, expressing in a nice, elegant way with statements about possible and impossible tasks. What are the requirements that a given dynamical law, a given physical theory must satisfy in order to support the existence of what we informally call information? And so we did that. And I think so that you will see that in the paper, there are a number of principles that express conjectured laws of physics, if you like, that express these regularities. The most important one of those, out of those principles, is the interoperability principle of information. And these principles work a little bit like the principle of locality or the principles of thermodynamics and so on. So they are like guiding principles that should also help us guess future theories of physics. And this is why it's so important to express them in a way that's dynamics independent. So we are not constrained by a specific theory that we currently use to describe the dynamics of given objects, but we can use the principles just like in the thermodynamic case, when we can use the second law of thermodynamics to rule out certain laws and say these are not acceptable because they violate it. In just the same way, we can use these principles of constructor theory of information to help us guess future theories of physics and possibly the success of quantum theory and general relativity.
Mm-hmm. Cool. So the constructor theory of information takes the abstractness or dynamics independence of classical information theory and has a way of expressing that for quantum systems, whereas standard quantum information theory is based on the dynamics, and then additionally draws this connection back with laws of physics, but in terms of these principles about what can and can't be made to happen rather than deriving it from the dynamics.
Yes, that's a very nice way of putting it. I think that's exactly how it is, in the sense that this is why it's so nice that somehow it allows you to access, I think, I like to think of it as a sort of hidden symmetry that's there in quantum theory and in quantum information theory, which is based on the idea of information, but allows you therefore to extract all the properties that are necessary for, in fact, I should say sufficient, not necessary, because we don't know if they're necessary, but I say they are sufficient for a system to display quantum information like properties without requiring this system to necessarily obey all the laws of quantum theory. And this is a difficult, I noticed when I was explaining these things, this is a thing that is often difficult to explain to practitioners of quantum information, simply because we are all used to just assume the laws of quantum theory and use them.
Mm-hmm.
But it's important to unpack what it is that, say, a unitary transformation, what are the properties of a unitary transformation or of Hilbert spaces that are relevant for information, distinguish them from other properties that are maybe just there as a convenient mathematical tool, but they're not necessary or they're not sufficient for the purpose of allowing information, for quantum information to be contained in quantum systems. In other words, what is it about a qubit that makes it capable of doing quantum computations? And one possible answer is to say it obeys the laws of quantum physics. We wanted to answer this question in a deeper way. So just not to refer to the whole of quantum physics, but just to say exactly what are the key transformations that you need to allow on the system for it to be capable of containing quantum information. And to do this in a dynamics independent way, in a theory independent way, so that this allows us also to imagine a different theory from quantum theory that has those features. And possibly this could be, for example, the successor of quantum theory in quantum gravity, or perhaps even beyond that, which is why we think this is exciting.
Yeah, cool. So can you give us an idea for how this kind of key property of qubits that's different to bits comes out in this dynamics independent way in constructor theory?
Yeah, so I think the key, so there is a key idea in a key property that's required of all information media, both those that are just classical, they can only contain classical information, and also those that are classical but also quantum, they have these extra abilities. And this property is the fact that they must have a set of states that can be copied perfectly. So if you have two replicas of the same system, obviously you can think of a bit, you must be able to copy a set of states of one system onto the other and vice versa. And also these states must be, it should be possible to permute them. So it should be possible to, for example, in the case of a bit, obviously you can leave the state as it is for the bit or change it into from 0 to 1 and vice versa. And you can generalize this to n dimensions. With a quantum system, there is an extra property that comes in that's very important. And we show that this is actually the root of all the properties of quantum systems. And this is the fact that these states that you can copy, that there are more than one set of states that you can copy. And these are the different, if you like, the different variables, the different observables of a quantum system. But if you consider these two of these two sets together, they can't jointly be copied. So it's impossible to find, there are some sets of states that cannot be all copied perfectly by the same machine. And this is obviously, in quantum theory, we know this is the no-cloning theorem. But I think in constructor theory, this is set as an axiom, if you like, or a requirement for quantum, for these more general kinds of systems, which we call superinformation media. So they are generalized quantum systems, if you like. And they must have this extra property, this non-copyability combined with the copyability of other sets of states. And it's actually quite surprising how by requiring this, as well as also requiring, imagining that the dynamical transformations that operate on these systems are deterministic, just like the Schrödinger equation is, you can get a long way into recovering the most distinctive properties of quantum systems, which is what we show in the paper. So in a sense, that paper can also be taken as a proof that the principles of constructor theory conjectures so far, including this interoperability principle, etc., are compatible with quantum systems, because we can use those principles to derive the most distinctive properties of quantum systems in superinformation media. But one thing that's important to say is that we're not deriving just quantum theory out of these principles. So this is a very different work from, say, other works trying to derive specifically quantum theory out of axioms. Lucian Hardis and others have worked a lot in these directions. We don't want to pin down quantum theory specifically, unlike what they did. We really want to basically extract this hidden symmetry in quantum theory, but still leave room for other theories to satisfy the principles while preserving the ability to perform quantum computation-like transformations. So I think this is, that was the tension that we're trying to solve, David and I, at the time. And that's the output of these efforts are in the paper. And I think the nice thing is that in this framework, you can also discuss things like probability as a derived concept as well. So things like the Born rule and so on, you can see that it can be derived from these higher level principles that are obeyed by some superinformation media. And again, these principles are phrased in a way that's dynamics independent, which is very interesting. So hopefully this is a way to also, as I said, to imagine a theory that's not quantum theory, but has the features of, supports the features of quantum systems to the degree that they can perform quantum computations.
Mm-hmm. Yeah, cool. So one of the things you mentioned there was this assumption of the dynamics being deterministic then enables you to derive these results. So do you think that tells us anything about whether dynamics have to be fully deterministic, or if there turned out to be some stochasticity somehow, would that then be incompatible with the Constructor Theory of Information research program?
I think, like in other cases of stochastic laws are not, so they are viable descriptions of given physical situations, but the way in which they would fit into constructor theory is that they should be regarded as either approximate or emergent theories that can be derived from a deterministic theory that's somehow lies beneath them. So in a sense, we would hope that, in fact, constructor theory could help in by using the principles of constructor theory, we could find some deterministic theories that could give rise to the stochastic theories, that some putative stochastic theory you have in mind, that would then, these deterministic theories from which you can derive the stochastic versions would be the things that comply with constructor theory. So constructor theory somehow requires always there to be some underlying deterministic dynamics, if you want to talk in those terms, that can be used in order to derive whatever stochastic law one has in mind. So in that sense, it always allows you to see probabilities as emergent things that make sense within a context that's deterministic. And this is somehow the way in which I also understand quantum physics. There are different ways of looking at quantum physics, but somehow you can always see that things like the Born rule and so on, they are secondary or add-ons on the deterministic structure of the dynamical laws of Schrödinger equation or whatever other equation you want to use for expressing your dynamics in quantum theory. And I think so this is if you like, it's a stance. It's part of a whole philosophical stance or view on what the laws of physics should be.
Mm-hmm.
And I guess this is true for most of, so there are different camps in physics. Some other people would like probabilities to be fundamental, but I guess in constructor theory, we take the other view. And what is interesting is that you can actually do this, so derive probabilities from axioms that are non-probabilistic, not just within quantum theory, but also within this more general framework of constructor theory, which somehow gives me hope, because whenever you can do things of this kind, it means that the stuff that you're dealing with is robust, in the sense that it's not just tied to a specific singular point of the theory, but it can be broadened to a set of other theories too. And that's nice, because it means maybe some variations would still allow you to have these properties. And therefore, it's not impossible. In fact, it's to be expected perhaps that, as I said, post-quantum theories may also have this feature that you can derive their probabilistic behavior or appearance from an underlying deterministic dynamics, which is interesting, I think, in itself.
Yeah, it's cool. And this is what you show in the Constructor Theory of Probability work.
Yeah, I think this is a follow-up work on the constructor theory of information, where I provided a set of sufficient conditions for theories that support superinformation, so this generalized idea of quantum information, for them to have a probabilistic structure that's like the structure that's provided by the Born rule. So if you like, it's a way to to generalize some of these arguments that you have within quantum theory to derive the bond rule from axioms that are not probabilistic to a broader context where you may not just be talking about quantum theory, but about more general theories. And in a sense, this is something that's an open problem. I've always found very interesting, the question of trying to connect things like generalized probabilistic theories, which are stochastic theories that, in a sense, that they are aiming at generalizing the probabilistic structure of quantum theory itself, to see whether they could be considered as stochastic theories that you can derive from underlying deterministic theories, which comply with with constructor theory of information principles. This is some work that we haven't done, but I think it's an interesting thing if you could see them as, in other words, as superinformation theories, just the phenomenological version of these underlying deterministic theories that comply with principles of superinformation. And I think this is an open problem, so that's an interesting question to analyze. But that's the kind of questions that this framework allows you to address. And obviously, the hope is always that one of these theories that we are talking about could be quantum gravity. So ultimately, why are we doing all of these things is because many reasons. I find them interesting. But I think in general, if you want to know what could this be useful for, at present, because we don't have a lot of experimental evidence to tell us where is it that we are making some wrong assumptions in the current theories. In fact, they're just confirmed by the experiments we have had so far.
Yes.
It's nice to have theoretical tools that allow you to guess different theories from the ones we currently know. And ultimately, these superinformation theories that you can study within constructor theory, which support the bond rule and so on, are a framework where you can imagine you could try to guess what a theory of quantum gravity could be like without using the standard paths of quantizing gravity that have been proposed so far. So that's a very interesting application, I think, of this work.
Yeah, cool. So one of the things you have mentioned is, partly that is not trying to derive quantum theory from these principles, but rather trying to express the laws that quantum theory and future theories should abide by. And you also mentioned earlier that that maybe standard quantum information theory doesn't connect with the fundamental laws as much. So I thought it might be nice to talk a bit about an example of one of these laws of physics, so the interoperability of information. Could you tell us a bit about what this principle is, and then how it relates to the kind of dynamics? Could it be derived in some way from the dynamics, or is it a kind of separate law about information?
Yeah, I think the interoperability of information is a way to express a property that we expect in most information carrying systems. So we usually assume it's there, but no one had bothered expressing it formally before. And if you look at it, it's very difficult to express within the dynamical law type setting, which is also why I guess it hadn't been expressed before. So the property is the fact that whenever you have a system that can contain information, in other words, it has a set of distinguishable states that can be copied, you expect that if you consider a different system that can also do the same, for example, a bit can be embodied by a switch, or by a flag of different colors or two different colors, or a traffic light that can switch between two different colors, etc., etc. So all of these are examples of bits, and they're all different. They have very different physics that underlies them. But we expect them to all be interchangeable in some sense. So if you want to make a communication system out of a number of different ways of implementing a bit, a switch, or a traffic light, or whatnot, then you can put them together and they will be interchangeable for the purpose of communicating the message you want to communicate. This is not that trivial as a property. If you want to express it as a property of the dynamics that these objects obey, it's not really a trivial property. In fact, it's an accident that all of the dynamics we know so far have this property. But it's quite a strong constraint on what the structure of the dynamics should look like. And in constructor theory, you can express it elegantly by saying that if you have two different information media, each of which has a set of distinguishable states, and you put them together, the combined system should still be an information medium, meaning it should still have this set of states that can be copied and permuted in all possible ways. This is a very elegant, short, simple statement. But if you look at what kind of constraints it puts on the algebra of tasks that must be possible on compositions, on the composed system of two different information media, the constraint is very tight. And it so happens that quantum theory satisfies this principle. Discretized versions of classical physics do too, but not all theories do. And I think somehow this is a way of expressing irregularities, the laws of physics that must be there for information to make sense. If we didn't have this principle satisfied, it would be very difficult to even think of what an observable is, to imagine what a measurement would look like in a dynamics where this weren't true. So for instance, there are models of the universe where you have different sectors that can't communicate with each other, dark sectors and so on, that would violate this principle, at least in the form that I've just stated. And the message is that in those universes, it would be very difficult to make sense of things like information processing at the global level, where you talk about both sectors together. An aspect that's also often overlooked is that this very principle is assumed by most theories of testability, of like when you think of a way of how to test a given physical theory, you want the physical systems that this theory describes to satisfy this principle for observations to make sense, for tests, for any kind of physical test where you're measuring an observable to even make sense and to be implementable. And so it's important, I think, to have this principle in mind when, for example, you're imagining a new theory. And an application of the principle was recently, we had an interesting way of using it in a context of designing some tests to test quantum effects in gravity. You can use it as one of the axioms to derive a certain theorem that tells us that if a given system has the ability to entangle two other quantum systems, then it must be quantum itself. This can be applied to gravity specifically. So if gravity can entangle two masses, then gravity must be quantum. But the way in which we prove this theorem, which is basically based on these axioms of locality and interoperability of information, is theory independent. And it's very nice because it's robust against changes of the dynamics that you're using. So you, especially in contexts where you think of quantum gravity scenarios, given that we don't have a single quantum gravity proposal that's been singled out as the right one, it's very important to have these theory independent arguments to make robust inferences about what to do in a context of a test, for example, where you want to test whether something is quantum or not in that scenario. So I think that's kind of an application of the principle. But in general, I think it's a nice example of a case where it's really difficult. If you think of I think David and I thought a lot about how to express it in dynamical laws. Mm-hmm. And it's much more easy to do it in terms of tasks. It's very elegant. You don't have to worry about expressing, for example, the details of the constructor that would change one system into another when you do a transformation where you copy the information from one type of system to another type of system and so on. It's all hidden in the statement of a certain task has to be possible. And it's quite elegant. I think it's very interesting, I would say, philosophical conceptual device.
Mm-hmm. Yeah. So I guess in some sense, it tells you more about what's going on than if you had this kind of complicated proof showing that that information from a certain system can be transferred to another system.
Yeah, exactly. So you could have a dynamical, this is a very nice point, that you could have a dynamical model where you say, I have some initial conditions, and according to these initial conditions, the dynamics says that I can make this transformation involving these two systems, which on reflection looks like copying some states from one system to another. That's one way of putting it. But this is very convoluted. You have to set the initial conditions, describe the dynamical laws, fix them specifically. Whereas in constructor theory, you can avoid all of that. You avoid mentioning of the initial conditions, you avoid mentioning the dynamics specifically, and you just put this requirement of what tasks you want to be possible on these two systems. And that in itself implicitly puts constraints on what boundary conditions you need for the systems in question, what kind of dynamics are allowed, and so on. but it's not the main focus of the theory. So the statement is broader and makes more sense at this higher abstract level, which is why it's useful in some contexts where the dynamical laws are not specifically known.
Yeah. And is it expressing these kind of laws that you were referring to earlier when you were saying about, drawing this connection of quantum information back with fundamental laws of physics?
Yeah, I think the early days of quantum information were, as far as I gathered from some of these nice stories that I've had from David and Arthur and other colleagues that they worked with, like Charlie Bennett or Seth Lloyd and so on, Vlad Kovedral as well. Somehow the focus was really to understand better how quantum physics works. And the key problem there was to figure out how to ultimately understand the measurement. What is an observation, and why is an observation or a measurement not problematic within a context where you consider unitary quantum theory is something you worked on as well. When you want to describe the measurement in a completely unitary way within the framework of quantum theory, without putting collapse variants or extra axioms that say you have to have a classical world outside of your quantum world. And somehow, so the emphasis was really to understand some of these basic information theoretic properties of quantum theory. Ultimately, the measurement, trying to fix the measurement problem, which I don't think is a problem anymore, but I think it was at the start, it was something that wasn't understood, was precisely to figure out the information theoretic structure of quantum theory. And that was the focus. It wasn't really that people were thinking, oh, how am I going now to provide an algorithm that's going to solve this specific problem for the sake of a given application. So initially it was really trying to, even the early algorithms, even quantum cryptography, Gilles Brassard as well, and Arthur Eckert, etc., they were all thinking about trying to understand how information theory works within a quantum system. And this has gradually been lost, I think, in quantum information research. I think there's been more and more a focus on maybe applications. I guess that's a natural evolution of the field. But I think the approach that was used at the time of using information theory guide to extract some basic properties of a physical theory is very much still useful as an approach. It's still very much needed within physics, perhaps not within quantum theory anymore, because I think we solved, it was these people, the quantum theory community has solved largely some of these problems. But in the context of different research, understanding, for instance, the physics of quantum gravity, imagining new tests of physics that go beyond the ones that we've been doing so far, which clearly are not probing the right things, because we keep noticing that the laws are okay with the confirmed by these tests.
Yeah.
And perhaps also understanding the physics of life. Even this is a much broader context, but going along these lines, you can think of the physics of the mind. So the way in which artificial intelligence, I think this idea of understanding what a mind is doing when it's thinking would benefit a lot from some of these physics and information theory-based approaches, but really directed to the fundamental level, not at the level of, oh, I want to solve this algorithm and I need to optimize a certain way of addressing a given task, but really trying to go back to these more fundamental problems that I think are still open, and perhaps we've lost a bit our focus on them. But I think we should regain it, because it's really important. They are the fuel for future discoveries. I think that's where the fuel for even future applications comes from. So we need to keep the fire alive there so that new ideas can come out.
Yeah. So it's like taking this information theoretic approach that proved really successful in solving problems in quantum mechanics, and then continuing to apply it to these fundamental problems.
Yes. And expand it and try to, this idea of constructors rather than computers, so trying to expand it even to areas where it's not just information and computation that's relevant, but more general tasks. I think that's what David and I found very interesting in developing constructor theory. And the hopes that these tools will be useful for these problems I mentioned. They've been to some degree so far, and we are hoping that more is to come in a sense.
Yeah, cool. So I wanted to come back to a point you mentioned earlier, that you mentioned a point that's often overlooked is the connection with testability and with making testable prediction. Could you expand on that and how it relates to this interoperability of information principle? And in what sense does it tell us something about testability?
So I think every time one performs a test in physics of a given physical theory, there's a moment where an observable is measured. And these observables are, if you follow the constructor theory approach, you can express them in a very general terms as a set of states that can be copied. Ultimately, the fact that in a theory you have observables, which are the things that are necessary for the theory to be testable because you need to perform observation of a given system, that fact means that the theory must allow for things like information media, or in fact, at least a set of distinguishable states, which I think we can approximate as an information medium and for the purpose of this discussion. So the fact that the theory is testable means that it must permit information media, which also means that it must comply with the interoperability of information. And if you give up these principles, you may still be able to imagine some kind of testing, but I think it would be very hard because this idea that the substrate of your measurement is interchangeable with any other substrate. So when you have a display that says, I really measured this and this thing on a particular system, you can change that measure device with a different one where you're using a different target as your display. So the display is made of something else. All of these things are simply assumed in the theory, and this is what the principle of interoperability requires. We never express it explicitly, but I think this is at the basis of the scientific method, of the fact that you can repeat experiments and make them in different forms here, there, and somewhere else. So I would say if you decide to abandon this principle, you would have to think very hard to imagine even how to measure a single observable on a system in a way that's reliable, in the way that we assume usually with the theory of testability. I think a similar principle that also is required when you talk about the test is locality. So the fact that you can divide the system in the universe in subsystems that are independent, and when you address a certain system in an experiment, it's really independent can be independently prepared and measured, is a property that's really necessary for making sense of a test. If you hadn't that property, again, it would be very difficult to make sense of a test, really. This is not really a proof, but I'm saying that I think there is a way to prove this fact that these properties are really necessary for a theory of testability. And no one really thinks about them explicitly.
Yeah.
But it's nice because sometimes you have theories where either locality or some other properties fail, and some of these theories are mathematically viable, so you can still make calculations and even dynamical laws that predict certain things. But then you have to ask yourselves, how am I going to test this? And often the answer is that you can't test them, which is the problem for a physical theory. They're still interesting, maybe mathematically, but I think they don't make sense at the physical level.
Mm-hmm. Yeah, cool. So the kind of intuition for why interoperability of information is needed for testability is that in order to measure properties onto measurement devices and have these consistent outcomes on different measurement devices, you'd have to have the interoperability principle because the property needs to be able to be instantiated, copied from the device onto your system that you're using to measure. Mm-hmm. And can you give us a kind of general intuition for why the principle of locality is important for this testability, or what might go wrong or becomes a bit strange once you don't have the principle of locality holding?
Yeah, I think the main problem is that when you, like a basic property of any experiment is that when you prepare a system on which you want to test a given prediction, you would like to be able to prepare the system and then let it evolve according to the dynamical laws that you're testing without it being affected by other things that you're doing on other systems. Unless these effects can be, of course, some of these effects can be there, but I think you would like to be able to isolate the system in such a way that there are no, for example, instantaneous actions at a distance, etc. Because if there were, then you would have to take those into account. And I think that would jeopardize the way in which you measure, for example, certain observables of the system in question once it's evolved to the desired state. So one aspect is simply the independent preparation and measurement of systems is essential to an experiment. And another aspect is that, for example, when you measure correlations between systems, this, for example, happens when you do, I don't know, Bell test within quantum theory. It's important to be able to, if you're talking about a pair of systems that have correlations and you want to check those, not just in quantum theory, but in more general theory, again, you would like to be able to say that when you measure one system, the other system stays unchanged as a result of this measurement. Whereas in a theory that doesn't have locality satisfied properly, this may not be the case. And this becomes difficult because then you can't even test basic correlations, which are fundamental. These are 2-point correlations are one of the most fundamental things that you need to measure within the theory. And I think the lack of locality would make these measurements very difficult. So somehow all theories we know satisfy these principles. The theories we trust so far are of this form. And it's reasonable to expect that future theories will too. Partly because then otherwise we would find them very difficult to test. And so in physics, it's important to be able to test theories because that's basically what physics does. I guess you want a theory to make predictions about certain experiments and be able ultimately to test some aspects of the explanations that the theory provides. And so I think testability is fundamental as a property of physical theories.
And does this testability in constructor theory almost come out as a nice consequence of having these principles of interoperability of information and locality, or is it formally involved somehow in the theory?
Yeah, this is a very nice question. I think David and I have discussed this a lot. I think David has a paper on testability of variety in quantum theory, which is specifically about quantum theory, but I think touches on some issues of what is required for a theory to be testable in general. And I don't think we have a formal proof that the axioms of constructor theory as we have them now imply necessarily testability, but I think it's reasonable to expect that the axioms or the principles of constructor theory information do imply that testability is needed in a theory that satisfies them. And that's because, as I said, if hoping that they work correctly as we expect them to do, they capture these regularities that are needed for observables to be possible, in a sense, for copyable sets of states to be embodied in physical systems. Once you have that, then testability should be a property that follows. We don't have a formal proof of this, but it seems reasonable to informally seems true. So it's a nice way of putting it, Maria, that you said now that you are automatically, if you have a constructor theoretic, a theory that complies with constructor theoretic axioms as we presented them so far, or principles, then it should be automatically testable, which is nice. It's a good thing, I think. By the way, I keep saying axioms or principles. I think I prefer to call them principles. Yeah. Because I noticed that, in fact, we noticed that some parts of the community is more mathematically oriented and likes the idea of an axiom. They work just like axioms in the proofs, but I think they have this extra ambition, if you like, to be laws of physics, a bit like the thermodynamics laws of physics. You can think of them as axioms as well. There is even an axiomatic approach to thermodynamics. But I think it's nice to think of them as really principles because they tell us something about the physical world. So I'd rather, whenever I said axiom, just think principles. That's a more accurate way of thinking them.
Yeah, because it's, relating back to this idea of that the principles are aiming to express additional physical content to what is in the dynamics rather than just expressing some aspects that they're consistent with, which is maybe the intuition that axiom gives.
Exactly. Yeah. Yes.
Cool. So I also wanted to ask about one of the kind of technical problems that is solved in the constructor theory of information, where you mentioned that there's this circularity in the definition of information in classical information theory in terms of defining information in terms of distinguishability, and this circularity emerging there that's solved in the constructor theoretic expression of information. Could you tell us a bit more about what that problem is and how it's solved?
Yeah, so the problem is that often if you try to define information in classical information theory, most of the times you don't worry about that, actually. To be fair, most people who use classical information theory, either in the way that Shannon, for example, did, don't worry about what is a set of distinguishable states. They just assume they have such a set of states, and then they use them for communication. And there are some rules about how this communication goes in a channel, etc. But no one bothers with the question of, like, what is it that these states what features do they have to display in order for them to be distinguishable? And now if you ask that question, then you start noticing that there is a little bit of circularity, because you say, okay, a set of states is distinguishable if you can maybe map it one-to-one onto another set of states that can also be distinguished. And then you realize that's not a good thing to do, because it's circular. Then you think, okay, never mind. Let's talk about then a set of states that can contain information. And then you say, okay, but the information is defined in terms of distinguishable states. So we can't get out of this. And unless one way out is to say, no, a set of distinguishable states is a set of orthogonal states, for example, in quantum theory. That's one way to cut this problem short, in a sense. But for us, it wasn't a viable exit, because we didn't want to use formalisms of specific theories. We didn't want to restrict ourselves to a theory where you have the concept of orthogonality between vectors, maybe in a theory that is different from quantum theory. You don't have such a concept. So we wanted to have a more general way of talking about distinguishability, and we didn't want to be circular. So in the end, we ended up with this idea of copyability. So the way you exit this circularity is to make a conjecture about what is it that distinguishable really means in terms of physical operation. And the closest we have, considering what we know about quantum theory, classical physics, etc., is that a set of states is certainly distinguishable if you can copy it onto another system. In fact, it's better to even think of a replica of the same system. So it's all self-contained, right? So you don't even have to postulate other systems to be there. You just consider a system, a set of states, and then you imagine a replica of it. And then you just define everything in terms of those entities, and a task that has to be possible on these two, one system and its replica. And the task is to copy the set of states. Once you know this, once you require this, assuming that you can create as many replicas as you like of this system, you can quickly, once you have a set of states, you can then copy them on a replica, then again on another replica, etc., until you create an ensemble, if you like, or you can get arbitrarily close to infinitely many such systems, all prepared in the same state, chosen out of this set of states. And that's the intuition behind requiring copyability, because once you have copyability on one system, together with the fact that you can replicate the system as much as you like, which is also, if you like, a requirement or some kind of approximation that's okay within information theory to assume, you know that you can get arbitrarily close to as many copies of the same state as you like. And this is it's one possible method to distinguish that state from another state from this set. Because once you have lots and lots of replicas of the same system prepared in one state, and then another set of these replicas of the same system prepared in a different state, the idea is that you can perform some transformations whereby these two ensembles can be distinguished. But you don't have to, this is just an informal explanation why this is a good idea. But this is not taken as a proof or anything. We just take as an axiom or an assumption that copyable sets of states are distinguishable. And that's one way of defining distinguishability without being circular. Once you have that, then you can build everything on top of that, which is nice. So that's how we got out of the circularity.
Yeah, by introducing this copyable task, and then that allows you to define things without the circularity.
Yeah, so for example, in a theory where you don't have orthogonality, because maybe some features of quantum theory are broken, for example, supposing place a dynamical law that does not admit Hilbert spaces, but still has dynamical transformations and things like that, then you can still try to identify states that are distinguishable, not by looking for what are the orthogonal states in the system, but by looking at what are the sets of states that we can copy according to these dynamics. And constructor theory would say that those are your information variables, those are the observables that you can use in order to perform a measurement on the system and so on. And it would also tell you that all the systems that, according to disputability theory, have these states that are copyable should also obey the interoperability of information. So they would have to have a certain way of being composed together, and there should be a certain algebra of tasks being satisfied and so on. So all of these things are ways of applying this approach to a scenario where you don't have the same structure as in quantum theory or classical physics.
Mm-hmm. And why is it important to consider these replicas and ensembles rather than just one version of the task with one replica of the system?
I think then it's not necessary for the theory. So it's not something that is needed to make sense of information. It's one of the axioms we use so the fact that when you have n copies of a state prepared on, let's say, a set of n replicas of a given system, and then you have a different state that's also prepared on say another set of n replicas of the same system. If n tends to infinity, you would like to assume that these two things are distinguishable in the sense of distinguishability that we just said. So this is not necessary for the theory of information, but we did assume it in our proofs. And it's a thing that is reasonable to assume in most theories of information that we've had so far. So it sounds like it's a good axiom to have. We call it the ensemble distinguishability axiom. It's not that important. So for the definition of distinguishability, you don't need it. It's more like an explanation for why copiability leads to distinguishability in a natural sense.
Yeah.
But I think it's not needed for the definition of information media per se. We did use it within the Constructor Theory of Information paper to prove some of the results.
Mm-hmm.
I suspect that if we relax that, then we would have a different kind of physics, but some of the results would still be possible to prove. Mm-hmm. So I wouldn't exclude the possibility of not having that axiom, and maybe there is a better axiom to rely on. So I wouldn't elevate that as a principle, really. It's more like an assumption that we're using for simplicity, also because it seems okay to use in most information theories we've known so far. But it may not be true. So maybe that's an open question, really.
Yeah, cool. Yeah, it's an interesting point to distinguish the assumptions may be used for convenience or of intuition, and then the fundamental.
Indeed, yeah. Yes.
Yeah.
Yes.
And yeah, so just to wrap up the discussion, I have a final question, which is about thinking about the future applications of constructor theory of information. Is there any particular problem that you are most excited about or interested in at the moment in applying constructor theory of information to?
Yeah, I think there are a number of problems. I think the most interesting ones to me are related to particular applications to some. So one application is the application to tests of hybrid quantum dynamics. So I think this is a problem I've been interested in for a while now. And my work on constructor theory led me, in a sense, in that direction, because it's an area where it's really nice to have these principles that are not tied to specific dynamics. Mm-hmm. The area is an area that's important for not just for fundamental problems necessarily, but also interesting for certain applications where you're thinking of a situation, even in the laboratory, where you have a system that's unified, a quantum system like a Qubits, so you know that you can use it as much as you like in all sorts of quantum ways. And then you have another system that either has a dynamics that's quantum but intractable. So this could be a macroscopic system with lots of degrees of freedom that you can't, you're not able to simulate adequately with some dynamics-based methods. So you don't know exactly what the dynamics does in a certain context when it couples to the qubit. Or it could be a system which is generally unclear whether it follows or not quantum theory. And this could be something that can collapse away from quantum theory. It could be gravity, where we don't know which quantum theory specifically to use, and so on. And so the combined system of this qubit and another system whose dynamics is unknown is a hybrid system. And there you can use lots of approaches. There are lots of studies on these systems. People usually either use approximations on the side of the problematic system, or they make some assumptions or they guess a specific dynamics for it. For example, you can have classical quantum hybrid dynamics. But I find it interesting to look instead at what happens when you apply constructor theory of information to it. So in other words, instead of assuming a specific dynamics, you just forget about dynamics for the moment, and you take these axioms or principles of constructor theory of information to be true for both systems. Because what you want to be still true in both, on the qubit and the other system, the mystery system, is that they both should have observables, they should obey the interoperability principle and other principles like locality, etc. So at that point, you can use these constructor theory principles of information to make predictions still, because you can prove no-go theorems. You can say, okay, assuming that these principles are true, then such and such a thing should certainly not happen. And one example of this is that we could prove under what conditions it is impossible to have a quantum system coupled to a fully classical system. So if there is a kind of coupling between these two sectors, the mystery sector cannot be fully classical. So it has to have some non-classical features in it. And this is some work that's very interesting that I've done with LOTCO, which then led to this test of quantum gravity effects, where the problematic sector is gravity. That's one of the applications. But there are many more applications. I think we can work in different frameworks where you can try to combine the constructor theory of information axioms with the thermodynamics, constructor theory of thermodynamics axioms, applied to this kind of context and see what kind of predictions you get out of that. So I see this as a very interesting, fruitful direction. And I think I'm really interested in developing this direction. And the other direction is the one I mentioned earlier, that it would be nice to look into populating the space of superinformation theories, where I said that these superinformation theories are a framework where there are some conditions under which you can show that these theories describe systems that behave much like quantum systems. Some of them satisfy this requirement that they can generate a Born rule out of certain assumptions. Mm-hmm. I would like to imagine a model for one of these theories, maybe inspired by GPTs, maybe considering that these theories should still be deterministic, they can't be GPTs, but they could be deterministic version of GPTs, out of which you can then derive GPTs under some assumptions. Mm-hmm. And again, this would be interesting because they would simply be good candidates to describe, going back to this problem of hybrid systems, this mystery sector in the hybrid system context that I said earlier. So this system that may not obey quantum theory, but has features of quantum physics in it. So I think that's a very interesting direction. And finally, I would like to use these constructor theory of information principles to understand some problems in quantum field theory, so this is some work I've been doing with LOTCO for a while now, partly motivated by the gravity problem that we addressed. So when you quantize both gravity and the electromagnetic field in this canonical way, you end up with a number of possible choices of what's called a gauge. So you can choose different methods to describe, if you like, your field. And some of these gauges are local, so they are better than others in the sense that they are more accurate as far as the physical description. But when you decide to quantize in some of these gauges, you end up with dynamical modes, dynamical variables in the field that are called ghosts. So they are there, they participate in the dynamics, but they are not supposed to be observables. The reason being that if you can observe them, then you violate this property of electromagnetism, and there is an equivalent for gravity, which is called gauge invariance. Now, the problem is that these ghosts participate in the dynamics, and although they are not observable in the standard sense of quantum theory, so they're not necessarily, they don't have a set of preparable states associated with them that are their eigenstates. They are still observable in a weaker sense. And I would like to use the constructor theory of information notion of an observable to understand what they are. Why is that important? It is important because it shows that there is some kind of inconsistency within quantum field theory at the level of what is an observable in this theory. This both even in the electromagnetic case. And I think this is interesting because it points to some issues at the foundations of the theory, which can be easily overlooked for most applications. But I find them interesting because I'm hoping that maybe by digging a little bit in this direction of inconsistencies, guided by the idea of information theories and constructor theory of information, you can actually find maybe an opening towards a different theory. Because I think quantum field theory is not really, it's a useful approximation to very useful calculational tool, but it's not very satisfactory at the level of what it explains physically. And I think we should be more critical about it and try to actually find a replacement for it, something that's not just a calculational set of tools, but it's really a proper theory, a proper explanation of what's going on. And I'm hoping that this principle of constructor theory of information can help with that.
Yeah, that's really interesting direction, because it's almost like before even expanding to considering the theory's more general theories, there's an existing problem in quantum field theory that you're trying to solve using the constructor theory tools, and that might then lend insights to these more general theories, but it's already a problem in the existing quantum field theory.
Yeah, and I think, okay, the last thing is, of course, what you've been working on, really the connection with thermodynamics. So there's a whole other chapter about constructor theory and thermodynamics, and there is a connection with information theory there. And I think it would be nice to dig deeper into that. So there are some early results in that direction, but I think constructor theory of information will be useful for that too. So to establish this link between information theory and thermodynamics that doesn't go through the second law, which is usually stochastic, but goes through the first law of thermodynamics, or in fact, the conservation of energy. And I'd like to understand that better. And I think these tools will be useful. So maybe something that you might be interested as well in the future. So I don't know, we can collaborate on that, or I think these are the main directions I can see at the moment.
Yeah, great. Yeah, they're all really interesting, and it's cool to see how the constructor theory of information is quite core to all of the other applications. Like, taking these ideas and then applying them in all these really wide-ranging contexts to wide-ranging problems across disciplines as well. Yeah, cool. So I think we can wrap up here. Thanks for the discussion. It was really interesting, and good to talk about all these aspects of constructor theory of information, and look forward to seeing how things progress in the future as well. So thanks for joining us.
Yeah, thanks Maria, for having me. It was great. Thank you.
Yeah, great. And thank you to our audience for tuning in. Feel free to leave comments, and you can also subscribe to my YouTube channel and other social media accounts for updates on more content on foundations of physics and quantum science and technology. So thanks for joining. Bye.
Thank you. Bye.
Okay.